Welcome to The Explainer, where we break down big topics. Today, we are diving deep into Boolean algebra, the hidden language that's literally powering our entire digital world. Okay, let's just jump right in. Take a look at these two expressions. On the left, you've got this complicated mess of logic, and on the right, a single letter. Now, believe it or not, these two things are functionally identical. Pretty wild, right? So, that begs the question, how in the world do we get from that mess on the left to the masterpiece on the right? Well, the answer lies in this incredibly powerful system of logic that was invented over 150 years ago.
And here it is, Boolean algebra, named after its creator, George Boole. Now, this isn't just some abstract math you might have slept through in school. Nope, think of it as the art of digital tidying. And it's absolutely fundamental to how every single computer, phone, and smart device actually works.
So, to really get how this all works, we've got to start with the basics, the absolute fundamentals. And that means learning the basic language of logic, which, you'll be happy to hear, is made up of just three simple operators. First up is the AND operator. And to make this really tangible, let's just visualize it with a simple circuit. I want you to imagine two light switches, one right after the other in a series. For that bulb to light up, you have to close the first switch and the second switch. If either one is open, that's it. The chain is broken and the light stays off. Simple as that. Next, we've got the OR operator. And this one is, let's say, a little more forgiving than the AND operator. So, let's picture those same two switches, but this time, instead of being in a line, they're wired side by side, in parallel. Now, the electricity has a choice. The bulb will light up if the first switch or the second switch is closed. It doesn't need both. And finally, we have the NOT operator. This one's the easiest of the bunch. It's just a logic inverter. It does exactly what it sounds like. It just flips the input to its opposite. Now, the circuit for this is actually pretty clever. The switch is in parallel with the bulb. So when the switch is open, the current has no choice but to go through the bulb, turning it on. But the second you close that switch, the electricity takes the path of least resistance, bypassing the bulb entirely and turning it off. It's a perfect physical example of logical inversion. Okay, so with those building blocks down, we can now get our hands on the magic weapons for simplification, and those are the laws of Boolean algebra. And don't just take my word for it. The sources out there really emphasize this, saying it's one of the most powerful tools in our entire kit, especially one of its less obvious forms, the distributive law. Yeah, one of the most powerful rules is this version of the distributive law that, let's be honest, looks a little weird. A or B and C is the same as A or B and A or C. Now, I know it doesn't feel as intuitive as regular algebra, but trust me, this rule is a key that unlocks some seriously powerful simplifications. So, the real magic happens when you start stringing these rules together. Let's just walk through the simplification right here on the screen. We start with the expression A and B or A and not B. Okay, first thing you notice, A is in both parts. So, using the distributive law, we can just factor it out. That leaves us with A and B or not B. Now, look what's inside the parentheses, B or not B. The complement law tells us that something or its opposite is always true, which we represent with a 1. So our expression just became A and 1. And finally, the identity law says anything ANDed with a 1 is just itself. And just like that whole messy expression boils down to a single A. Okay, this seems like a really neat math trick, right? But why does any of this actually matter in the real world? Well, let me tell you, the payoff is absolutely enormous. It is the reason our technology just keeps getting better. See, every single logical operation in a computer chip, it corresponds to a real physical thing called a logic gate. So simplification literally means we can use fewer physical parts to get the exact same result. And what do fewer components mean? You guessed it. Lower manufacturing costs for every single chip that gets made. And that scales up to billions of devices. And it gets better. With fewer gates for an electrical signal to travel through, the calculation happens faster. This is how we crank up a processor's speed and cut down on lag. So let's just sum it all up. This simple act of logical tidying leads directly to circuits that are smaller, cheaper, faster, and way more power efficient. This isn't just theory, folks. This is the engine of technological progress. Before we finish up, I want to look at two really elegant, kind of pro-level concepts that show you the deep beauty that's hiding inside the system. First up is duality. And it's just a fascinating principle. It says that if you take any true Boolean statement, like the one on the left, and you swap all the ands for ors and all the ors for ands, the new statement you get is also guaranteed to be true. It's this perfect, beautiful symmetry that's built right into the fabric of logic itself. And for what I like to call the ultimate cheat code, we have the redundancy theorem. This gives us a rule for spotting and just straight up eliminating entire chunks of an expression that, it turns out, contribute absolutely nothing to the final answer. It's pure waste removal. And this is the theorem in action. In an expression that follows this specific pattern, that BC term in the middle, it's completely unnecessary. It can never, ever change the final result, no matter what the inputs are. And Boolean algebra gives us the tools to prove it and just confidently get rid of the junk. And that really brings us to a final thought. We have just barely scratched the surface of a system that's designed to turn complexity into beautiful simplicity. It's happening billions of times a second inside every device you own. And it just makes you wonder, what other elegant rules like this are hiding in plain sight, quietly making our whole world work?